over to you. Right, we're good to go. I'm not sure we can hear you. Hey, Rob, you're not audible, if you can hear me.
On mute. That that would have been embarrassing to record the entire thing on mute.
Yep,
Welcome to building stateful workloads in Kubernetes. Am I off mute now? Can you hear me okay?
You're off mute. When I've recorded like some of my clips for Pluralsight courses before, yeah, I've recorded the whole 7-minute clip and then I get to review it and then found out that I was on mute, which, yeah, not so happy.
Yes. I've done that as well. I've done an entire hour talk on mute and I'm like, well then, I will be doing this again.
Oh man, that must be like some eye-opening.
Yeah. So let's dig into building stateful workloads with Kubernetes. We're going to talk about getting the rest of the application into Kubernetes, not just the Kubernetes 101 talk or the Docker 101 tutorial, but how do I get the rest of the app in place? Here's the part where I tell you, I am definitely going to post the slides on my site tonight. I've chased similar speakers and had a really tough time getting them. So the slides are actually online right now. Let's head to robrich.org and take a look at the slides. I put them in chat as well. When we go to robrich.org, we can click on presentations here at the top, and here's building stateful workloads in Kubernetes. The slides are online right now. While we're here at robrich.org, let's click on About Me and learn some of the things that I've done recently. I'm a Jetpack developer advocate. I'm a Microsoft MVP, MCT, a Docker captain, and a friend of Redgate. AZ GiveCamp is really fun. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver completed software to the charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp, or if you'd like a GiveCamp here in Chicago or wherever you're watching this video from, hit me up on email or Twitter and let's get a GiveCamp in your neighborhood too. Some of the other things that I've done, Pro Microservices in .NET 6. I got to work with Sean and Matt on that book. That was a lot of fun. It just came out. And one of the things I'm particularly proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woo! So there's my claim to fame, my coveted .NET Rocks mug. And if you'd like a .NET, no, I'm just kidding. So let's dig into building stateful workloads with Kubernetes. We talked about this guy. Let's first start with stateless Kubernetes, because that's where all of the Kubernetes 101 tutorials leave off. We've got an ingress that maps DNS to a service. A service will load balance across all of the containers. Each container is wrapped in a pod, and we probably have a deployment that gets these things in place. Yep, that's the conclusion of all of the Docker and Kubernetes 101 things is ingress maps to service, service maps to the pods, which each contain a container. We got this. This is pretty easy. But how do we get past this? How do we get the rest of the application in place? Now, our applications probably look more like this, where we have our ingress, but our ingress has some configuration details, an HTTPS certificate, a domain that it needs to map to. We need these configuration details in our ingress. We have a service that maps to our pods, probably launched by a deployment. And then we also have file storage. So this file storage is really interesting. We want things that are more durable, where our pods, our containers are stateless. So if I reboot a container, I've lost all of the information within it. A volume gives us more durable storage there. But I might need things like the path to that volume, authentication details. Here's some configuration details. I also may have a database. Now, I need each of the pieces of the database to be able to communicate with each other so that they can keep that content up to date. And I probably need some configuration details to get into that database as well. So we can see that our application is a lot more than just a simple ingress to service to pods that wrap containers. We've got more moving pieces. Let's talk today about how we get the rest of this content into Kubernetes. So let's talk about state. Here's some states. These are not the states that we're going to talk about today, but yeah, there's some states. We're going to talk about this kind of state. State is living beyond the current lifetime. So for example, if we have a method and we need our values to live beyond that current method, we might put properties inside of our class. Now we can save our data into those properties in the class, and when we call the method the next time, we now have saved that state beyond the method call. By comparison, we might have other types of things. Maybe we have a request. So a request and response, a web page load, and we want to click save and then click the list and get those new details. So we probably have to move that content out of the web server into a database. Similarly, if we upload a profile picture, maybe we're saving it in the app data folder. What if we reboot the server between requests? So now that app data folder was part of that container and it just disappeared. We need something that is a little bit more durable. So let's move these maybe to Azure Blob Storage or maybe to our SAN and get those things out of the container to a more durable spot. Each of these are instances of places where we need to live beyond the current lifecycle, the current request, the current function call, beyond the current scope. So in Kubernetes, we'll see lots of different instances of this. We'll look at 5 major mechanisms here. We will look at configuration, secrets, data stores, file stores. We kind of talked through each of those scenarios already. And let's also look at singleton services. Let's double click in there and learn some more about that. So a singleton service. If I'm running a month-end report, I need to see everything for the entire month. So if I'm computing that month-end report, no other instances of this thing can be writing those report details or updating content within this month. I need all of the details for this month. How about an auto-incrementing primary key? If we have multiple instances, each incrementing the key, then they have to coordinate with each other, or maybe they might create duplicate primary keys. These are examples of singleton services where it needs the entire content of the domain to make a choice. Now in Kubernetes, we've chosen to outsource our hardware. We're creating containers that virtualize our operating system as well. And so because we don't own that, it isn't durable, we can't depend on it. So we need a mechanism to be able to create these services that can communicate together and, well, vote on who is the main instance to be able to do these types of computations. And then when that main instance goes away, the others can hold an election to create a new main instance. In Kubernetes, we're going to look at configuration, secrets, data stores, file stores, and singleton services, and the mechanisms that we use in Kubernetes to make these happen. But before we dig in, any questions so far? Any thoughts or concerns about the types of state that we're looking for, or what a stateful versus a stateless instance is? Excellent. Let's dig in. So the first thing that we'll look at is kubectl get all. Now, the cool part about kubectl get all is it returns all the resources. Kind of. It returns all of the stateless resources, pods, deployments, services, ingress, but it's specifically designed not to return stateful resources. The design of kubectl get all is that it specifically wants to avoid showing you things that if you deleted and recreated would not be identical, which is pretty much everything we're going to talk about today. So yes, kubectl get all does not actually return all, it returns stateless things. And as you grab these slides from robrich.org, you can click through each of these issues and understand people who have struggled with that. They've actually talked about deprecating all since, yeah, all isn't really all. So how do we actually get all the things? Well, if we say kubectl API-resources, it will give us a list of all of the resources within our cluster. So let's use that. And when we say kubectl get, we'll get the particular thing. So for example, if I only wanted ingress, I would say kubectl get ingress. If I only wanted pods and services, I would say kubectl get pod, comma, service. And we'll do that, but we'll get all of the resources. So here's the script. We'll say kubectl API resources. We'll pipe that to awk to only get the first thing. So we don't get the descriptions of these things. We only get their name. Then we'll grep out name, which is the title, that top one. Now we have only the unique resources. And then we'll pipe that to sed, replacing carriage return with comma. Now we have a comma delimited list of all of the resources in the cluster. And the beautiful thing here is it's not just the standard resources, but also the custom resource definitions that we might have pulled in from a service mesh or from other utilities that we've built. This is a list of all of the resources currently in this cluster. So now that we've gotten that list, let's pipe that into kubectl get this comma delimited list, and now we can actually get all of the things. That was a long walk. So yeah, ultimately, I usually create a shortcut, kubectl get -all, that allows me to run this script to be able to go get all the custom resources and run the get for all of those things. This script actually came from this post. So as you grab these slides from robrich.org, you can either copy this into your bash profile or your PowerShell profile, or you can reach in here and grab it from this GitHub issue. So yeah, kubectl get all does not actually get everything. It only gets stateless things. Let's talk about volumes. Volumes are a mechanism for persisting data outside of a container. It's great for file storage. What we can do is we can take a path, perhaps that path is on our host machine or in Azure Files or in Amazon S3 or maybe on our SAN, and we'll map a path from that external storage as a symlink or a junction inside of our container. The cool part is that the container knows nothing about this external thing. It just thinks it's a regular folder inside its file system. But if we save files into that folder, they're actually saved to much more durable storage. That's really cool. If I restart the pod and reconnect the volume, I now have those things. So for example, if I'm uploading my profile picture, I'm not going to save it inside the app data folder. I'll save it to a volume. Now, maybe I've mapped a volume into my app data folder, so I don't need to change my application. But ultimately, yeah, now that's more durable. Restart the pod, and I still have those images. One word of caution here with this, though, is that file locks don't work. Because the pod doesn't really understand that this isn't a local folder, any of the file locks that it builds are local to this pod. So for example, if two pods, two containers, map themselves to the same volume, the same folder on our external resource, then it would be easy for one to overwrite the other's file. So we'll need to build some kind of naming convention so that the pods can keep their own separate spots. Or perhaps we say only one pod can write to this volume, and the other pod needs to get a different volume. Let's take a look at the YAML of how we might build this. Now, we have a pod definition. This pod definition could be part of a deployment. And here's the YAML that we have so far, where we map this to a particular image and version. We might give it a name. We might have other properties here. And then here's where we're identifying the volume mounts. So here in the volume mount section, we'll give it a name, and we'll give it the path in the container that we'll symlink into. So if our application just goes to this path in the container, it's just another folder in our application, and we can read and save files there. Now we'll take this name, and here in this volume section, we'll define where that actually goes. Now we can choose various drivers. In this case, I chose the host path driver, which will create a folder on the machine, the Kubernetes node. And that's great for development and testing. But if I want something that goes across all the nodes in my cluster, all the machines, then I would probably need to pick a different driver. Maybe I'll choose Azure Files or Amazon S3 and store the content there. Now, in this case, host path is really good for testing, which is why I've listed it here. So here's the path on my host where that data will be stored. So any files stored into this folder will actually be stored into this directory. And now I can back this up in the normal way, and I can keep those files safe across pod restarts. So this is great. We now have a more durable place to store this data. It's outside of the pod in this folder on our host. So then the magic question is, who owns this file, this pod definition? Should developers own it? Should operations own it? If we're in a small company where we're wearing both hats, maybe this pod definition is great and we can just move on. But if we do have a larger organization, we have a separation between developers and operations, then we might hit conflicts. We've probably hit similar conflicts in our web.config file, where operations wants to be able to tune various things and developers want to tune various other things. And so we have this conflict over this file. In this case, operations probably wants to identify the driver and the path so that they can make sure that that's organized nicely, it's backed up correctly. And developers want to maintain the rest of this file. So can we split this file in half? Let's do that. Here's our container that includes that symlink into that particular path. It's wrapped in a pod. Here's our storage. Maybe that's Azure Files, maybe that's Amazon S3, maybe that's a folder on our host volume. Let's carve that storage into little pieces. We'll call each piece a persistent volume. And now we'll claim one of those pieces. We'll call this a persistent volume claim, and that will be the thing that we map into our container as a volume. We have storage, persistent volumes, persistent volume claims, and volumes mapped to our container. The beautiful thing is we now have this nice delineation between operations here on the right and on the left, and development here on the right. Developers can own the persistent volume claim and how it connects to the container. Operations can own the storage and how it's carved up into persistent volumes. We can create this separation so that we can create an elegant separation of duties across our Kubernetes resources. So let's see how we might do this. Here's that persistent volume definition. Similarly to what we did previously, we have the host path driver and we've specified the folder on our host path. We could swap this with Azure Files or S3 or a SAN. And we'll also specify other details. In this case, we have storage class name of manual, capacity of 10 gigs, and access modes of read write once. That means only one pod can connect to this to write, but it does have write permissions. We also have read write many, where many pods can connect and write to this, and read only, where many pods could connect, but they can't write to it. They can only read. So we've defined these details and we've given a name of PV volume and any other labels that we have inside of Kubernetes. Here's our persistent volume. We've carved up that storage into pieces, and this persistent volume piece says, I'm 10 gigs and read write once. Next, we'll define a persistent volume claim. Now, these are the details that the container needs in a storage. So we're going to say we have storage class name manual, access modes, read write once, and we need 3 gigs. Well, really, we need 3 gigs or more. So because storage class name matches and access modes match, and the storage is this big or bigger, then our persistent volume matches, and that's the one that we'll use. You notice that this one has PV claim, and we didn't specify the other one's name anywhere. We just find a match on all of these resources to be able to grab a particular persistent volume. Now that we've claimed that persistent volume in this persistent volume claim, here in our pod definition, the container definition is unchanged. We're still specifying this as the volume and mapping it to a particular directory inside of our container. But as we define how the volume works, rather than saying host path here and giving it the actual path, we'll say this is a persistent volume claim, and we'll give it the claim name. The name that we defined it right here, PV claim. So now PV claim is our definition of how to store this volume persistently. And the PV claim identifies these characteristics, and that maps to a particular persistent volume that operations can use to organize that content really nicely inside of the NAS or the SAN or inside of our cloud storage environment. So we have those pieces: storage, carved up into persistent volumes. We'll claim one of them and map it into the container as a volume. Ops gets to own this side. Dev gets to own this side. Any questions so far on volumes?
Here.
David, I'm curious, all equals sum. Which one did I say incorrectly?
No, that was the get all command that you had
yes.
earlier. Right, yeah. So all is not really all what you were saying. All only gets you some.
Yep, all get some. Because words are hard.
Why would we want to make people fall into the pit of success when we can make them fall into the pit of frustration?
Yes, exactly. Next, let's talk about config maps. Here's how we can do configuration inside of Kubernetes. Now, if we have a Docker compose file, perhaps we're specifying the configuration details there. If we have a Docker run command, we've specified the details of the configuration, perhaps as environment variables inside of our run command. And now let's see how we might do that inside of Kubernetes. When we're doing this configuration, these are read-only configuration details. We can mount them either as environment variables or as files. Now that's really cool. If we mount it as a directory, then our application can just list the files in that directory, open each one, and read the configuration value out of that file. By comparison, if we set it as environment variables, then in C# we just have to grab the environment that environment variable name, and we can pull it into place. Or even better, if we're using some of the ASP.NET templates that automatically pull in environment variables, then we just look into our iConfiguration object and they're just there. So how do we build these inside of Kubernetes? Well, we have a YAML file that describes this configuration. Now, this is a pod definition. Maybe it's a pod definition inside of a deployment template, or maybe it's a separate pod definition. We've got our standard configuration. Maybe we have other configuration like volumes. And then we list our environment details. Here's the name and here's the value. Now in a Docker compose file, we have name:value. In Kubernetes, we have name and we specify the name, and we have value and we specify the value. So in my application, I can just read into my environment and go grab these environment variables, and that'll give me the configuration. Now that's great. We've been able to set some configuration that our application can use, but again, who owns this file? Now, if we have a small business where we're all wearing multiple hats, maybe we don't need this separation, and that pod definition we just built is completely fine. But maybe we do have a separation between developers and operations, and we need different teams to own different pieces. So should we argue about the web config file? No, we can create a config map. Now, the cool part about a config map is this is just a dictionary of keys and values that identify the various details for this configuration. So we'll give this config map a name. This is the config map. And then we have the keys and values, So I've got a secure database. I've got logging enabled. I've defined my API URL. And these are just the keys and values inside this config map. Let me just grab one note there. There we go. So we've got the keys and values inside this config map. Now, how do we map this into our pod? We can do that here. So in this case, rather than enumerating each one, I just said end from, and I gave it that config map reference. So everything inside this config map will now get mapped into place as environment variables in my application. So my application, maybe I have a node app, so I say process.env and I dot that name, and I can be able to get at that configuration detail. Now I might have other details. Maybe I have volume mounts. Maybe I have other details associated with my pod definition. But now I have this elegant separation. Operations can own this piece. We can set environment-specific configuration inside of each namespace. And developers can own this piece, where they just identify, I would like to suck in all of the configuration from that config map and make it available to my application. This can be great if I have different configuration between dev and QA and prod. I'll create lots of different config maps, but then I'll have one pod definition that just pulls in the details from that from the applicable config map given the namespace that I'm in. I can also choose to map this not as environment variables, but as files. So my application could just open up a particular directory, enumerate all the files in that directory, open up each file, and get the config value. Much like we defined volumes previously, I can just name this one the volume. I'll give it the path inside my container. And then as I define what is that volume, previously we said use a persistent volume or host path. In this case, we're saying use a config map. Here's the config map, and that makes this path read-only, but my application can just enumerate all the files, open up each one, and get it. So now, how might I do this? So when would I choose environment variables versus files? Now, ultimately, it doesn't matter. I might choose to make some files, some environment variables. I might have a policy where I really like environment variables within my organization, or a policy where I'd rather read those files each time. And so you can choose which one makes the most sense for you. Either one works. I tend to find environment variables to be a little bit more discoverable. As I'm cruising through this pod definition, it isn't immediately obvious to me that this volume is configuration and not storage. Yes, if I read the rest of the YAML file, I would see that, but I tend to prefer environment variables as a good default. So that was config maps, but some of the configuration that we might have could be secrets, an API token to an external service, or a password into a data store. Those things we probably don't want to just store as environment variables where people can pull them out of either the YAML definition or just out of the environment variables in our application. So let's define secrets. Now, starting in Kubernetes 1.13, they added an option to be able to encrypt these secrets at rest. We're currently on 1.18, 1.16 is still supported, but that's not too long ago. It's the option. But if you haven't enabled this option, then your secrets stored inside of Kubernetes are only base64 encoded. Encoded and encrypted are different. And because every secret needs to be available on every node inside of Kubernetes, in case a pod that needs it gets scheduled there, then if you lose a node inside your cluster, if one of the nodes in your cluster gets compromised, it's safe to assume that all of your secrets are lost and you should rotate all of the keys. Now, that does sound a little extreme, but yeah, Kubernetes secrets are not stored encrypted by default. If you enable it, now they're encrypted, and so if you rotate the keys, then that encrypted data is now worthless on the lost volume. So it's closer, but it's still not great. So how would we create secrets? Well, we can create secrets using the YAML definition like this. Similarly to config maps, we give it a particular name, and then we have keys and values to define the particular pieces of this secret. Now, it's possible to define these in YAML, but I would choose to avoid them in YAML because it's far too easy to accidentally commit this file alongside the other YAML resources and lose control of those secrets inside source control. Instead, we can create them on the command line. Now, I grant that here you might have to then purge your bash history, but I find this to be a little bit safer way to create those secrets. I'm giving it a particular name, and then I'm creating the keys and values that I want inside that secret. Now, I can choose to base64 encode them rather than just providing literal values, and that might be helpful if I have carriage returns in my secret value. But in this case, we just have strings, so we can say from literal and give it the username equals the user and the password equals password. And now we've defined these two keys inside the secret named DB connection. So then how would we map? Yep.
So how is it encrypting the secrets? I mean, right? Because it's great to encrypt something, but then the problem becomes that you have to protect the key, right? Because if somebody gets the key, then they can, in some ways, it's just kind of moving the problem. So
Yes.
Yeah. So how does all that work? Not to send you too far down another path, but just curious about that. So
By default, it is base 64 encoded. Oops. If you
well,
choose
no
to
one will ever figure that out. But in case they
exactly.
do, yeah.
If you choose to enable it, you can encrypt it in ways, and I think the key is actually stored in etcd, which is kind of interesting. But at that point, it's like, okay, so if I lose etcd, then did I lose my secrets? And that's where ultimately, if you really want something to be secret, you may choose to put it in, say, Azure Key Vault or HashiCorp Vault, and get your application to go reach into that vault to go grab the secret. Ultimately, secrets in Kubernetes aren't very secret.
That's what I was wondering, because like I say, if it's kind of on the machine, right, there's kind of a way for somebody to get to it. So
Exactly. And since the application needs it decrypted anyway, if I launch a container that just happens to map the secret in an elegant way, then
bingo.
I got Kubernetes to unencrypt it for me.
Rob, can we keep these secrets in like Azure Secrets or like HashiCorp? They also have kind of similar option. Is it possible?
We definitely can. There's an
Okay.
option to be able to provide a Kubernetes provider that will connect to, for example, Azure Key Vault or HashiCorp Vault and pull the secrets from there. So instead of getting stored inside of Kubernetes at rest, they're stored inside of Azure Key Vault at rest.
Fabulous.
But at the same time, Kubernetes is sucking it from Azure Key Vault, storing it in memory inside of Kubernetes, and making it available unencrypted to all the pods that ask for it. So it's still not super secure. If you want really secure access to Azure Key Vault, leave Kubernetes out of it and get your application to reach directly to Azure Key Vault and pull that data straight out of Key Vault, and leave Kubernetes out of it.
You mean don't use Kubernetes at all?
Don't use Kubernetes secrets. Still use Kubernetes for scaling your pods, but just don't use Kubernetes secrets.
Got it. Thank you.
Yeah, the other issue though is that you still have to connect to your Key Vault, right? Whether that's from Azure or AWS or wherever. And if you're running locally, then you'll have a secret to connect to that. If you're running in Azure, you can do it with a managed identity. But see, secrets are hard.
The vault?
I mean,
you can't store it in the vault.
Right. So.
It's still better than having it in source code.
Yes, exactly.
And
it's
written
not
on
in the deployment mechanism, so it isn't in our source code. So if right now you're hard coding your secrets in your source code, Kubernetes secrets are definitely a step up from there. This was great. I'm glad we got to dig into how Kubernetes stores secrets and alternatives to that. I actually have a whole nother talk that talks about, so how should I store my secrets and what are the downsides to each approach? I agree, David. The problem with application secrets is they tend not to stay secret, especially when I create an environment endpoint in my website that allows any JavaScript app to consume them. I made that mistake exactly one time.
Well, and you think about, right, people, they get a secret, maybe out of the Azure portal or AWS console, whatever you're using. And they put that in Teams to send to a colleague to, okay, I need you to configure this, or they put it in an email. Well, if you work for any Fortune 500 corporation, I mean, really anywhere, because everybody uses M365 now, right? All that email is logged, right? I mean, all your Teams conversations are logged somewhere, even if you delete that message, right? I mean, and what is it over in Russia? They call it the FSB. Unfortunately, they're not stupid, right? They know these things too.
Yes.
Yeah, they're pretty crafty, unfortunately. So.
Right. Keeping secrets secret is way hard.
Yeah.
So how do we map these secrets into our pod if I haven't dissuade you from using them at all? It's actually surprisingly similar to the way that we can do it with environment variables. And so we'll actually see pretty much the same syntax. Now, in this case, I chose to mount it as a volume. So here's the path to my directory. I'm going to mark it as read-only, just to kind of emphasize that no application, you can't write secrets, but of course they're read-only anyway. And then as I define how that volume works, I'll just point it at that secret name. So inside this directory, because I've defined my secret this way with these two keys, then inside this directory, I will have two files. I can open up each file, read the contents, and get at the value. I could also put it in environment variables. And previously, we just said end from, and we sucked in all of the keys. But in this case, I'm going to enumerate each key that I want to grab. Here's the name, here's DB username, and I'm going to get the value from this secret key reference with this name and this key. So you can see that the key in the secret was called username, but I want that environment variable called DB_username. So that's a cool trick to be able to rename it on the way through. Similarly, I'm going to grab DB password from the secret named DB connection and the key of password. So now in my application, I can just reach into those two environment variables, get the username and password to my database, and I can use that to log in. Now, our environment variables secure in my application. Anyone who has access to kubectl can get that pod definition to get where those secrets are stored. And anyone with access to the process can just read those details out of the environment. So they aren't super secure there either. So I've got my secrets mapped into my pod, and now I can read them in interesting ways. Any questions about secrets or config maps or volumes before we dig into the next part? So we've handled a lot of the stateful pieces. We've handled how do I upload my user profile picture and keep it beyond pod restarts. We've talked about configuration details that I might put into my application, such as what is the name of the data store or the name of the environment. Maybe we're setting our ASP.NET Core environment to production this way. But what about data stores? How do we get multiple instances? That's where we dig into stateful sets. Now, the cool part about a stateful set is it's not that unlike a deployment, but it has very predictable names. So as pods spin down and spin back up, we will get the same pod name so that we can discover the other pieces inside this stateful set. Now, as we start talking about stateful sets, we'll probably start talking about clusters, an ELK cluster or a SQL Server cluster. We also have a Kubernetes cluster. And so the term cluster is now overloaded. The ELK cluster is made up of various pods running inside of Kubernetes nodes inside the Kubernetes cluster. So I'll try to avoid the term cluster as we've talked through stateful sets, just because it is so confusing. But I want to have a bundle of machines. I want to have a bunch of machines that can communicate together. And I use the term machine loosely because they're containers, they're not servers. But let's imagine an ELK server where I want to have lots of different shards that each work together to keep track of all my data. Now, each of the shards needs to be able to discover each of the other shards so it knows what data it needs to push or pull from, so that it can hold raft elections and pick which one is the main element inside of my bundle of machines. It's basically a deployment with predictable machine names, predictable pod names. So I might use it for Kafka, for ELK, for a database cluster, anything where I need lots of different pods communicating together to be able to store this stateful data store. So I have my containers inside of my pods. And so the container is named whatever the container is named, but my pods now have predictable names: pod 0, pod 1, pod 2. So if pod 2 wants to communicate with pod 0, it can reach through this headless service to get to pod 0. Pod 0 wants to communicate with pod 1, it can reach through this headless service and do this. Now, it is a service. So like any service, we could reach into the service and load balance across all these pods, but it is a headless service. So probably we don't want to have inbound connections here, but it is definitely possible. It is a service. Let's take a look at the YAML to build a stateful set. Now, if you're looking really close, it looks pretty much like a deployment. We have the replicas, we have the template section that defines the details of our pod. Here's our pod definition. In this case, it's an Nginx Alpine image. We mapped some ports, we give it a name. The one place where it differs from a deployment, other than just its name, is that it has this service name. That's the name of the headless service. So next, let's go define that headless service. Now, this looks like any other service that we would build that would load balance across all the pods that the deployment spun up. We have our name and labels. We have our selector. Here's the part that makes it a headless service. We say cluster IP of none. Excellent. Now that we've given it a cluster IP of none, it's not going to get a cluster IP. It's not going to get a node port. It's not a load balancer service. And so it hopefully is not accepting inbound traffic from outside. So how do we get to it? Well, if we just curl that service, then of course we'll load balance across all of the instances within this service, much like any other service would. But if we say the db1.db service, now we're hitting a particular machine within the stateful set. So for example, if the machines want to communicate with each other, they can use this DNS mechanism to be able to discover those other machines. Now, somewhere we probably have to keep track of the number of replicas, but outside that, yeah, I just curl those other nodes in the machine and I can start to communicate between these nodes. So that was pretty cool. When we first began, we had just a simple ingress and service and pods that hosted containers. That was kind of where our Kubernetes 101 experience left off. But we saw that our application had a lot more details. Now that we're familiar with config maps and secrets and volumes and stateful sets, we can take a look at this diagram and understand all the pieces that go into this. Perhaps our domain is a config map. Perhaps our HTTPS certificate is a secret. We'll map those into our ingress. Our pods may need to reach out into a data store, so we might have some configuration or secrets that we use to connect to that data store. We might have details of our file storage, so we'll use volumes for that. Now, maybe the path and authentication is not necessary to reach out to an external data store. Maybe we just map those as details inside of our pod. So we'll map in we'll have a persistent volume that carves up our storage. We'll have a persistent volume claim, and we'll map that into our container as just a directory. Now the container just knows it can read and write to this one magic directory, and things will persist off to that file storage. Similarly, if we need a database cluster where lots of different machines, pods, can communicate together, we'll use a stateful set. We'll have a headless service that allows them to communicate together, and then we might have a separate service, not unlike this service, that just exposes that cluster to outside consumers. So they grab the service, that gets them to the cluster, round robin across the nodes, and then as I persist the data into this cluster, then it can use Raft protocols or the headless service to be able to push data across the various shards. Config maps, secrets, config maps, persistent volumes and persistent volume claims, stateful sets. We got the rest of our application into Kubernetes too. All of these stateful resources allow us to move that next level into Kubernetes. Now in production, we may choose to use, for example, Azure SQL. Let them handle the details of our production cluster. We may choose to use Azure Files. Let them handle backup and restore and point-in-time restore. But we may choose to also put these inside of pods inside of Kubernetes and keep track of those resources ourselves. Perhaps we're on-premise and need those resources inside of Kubernetes. Now, once upon a time, we were given the rule, never put SQL Server inside of containers. Only put it, never put it inside of virtual machines, only put it on bare metal. Today, our guidance is Never put it in containers, only put it on virtual machines. Tomorrow's guidance will probably be put SQL Server inside of containers and map SQL Server's persistent storage into volumes that get saved beyond pod restarts. I suspect in the medium time, our content will be running inside of Kubernetes if it isn't running inside of a hosted service like Azure SQL Database. So that's the rest of our application inside of Kubernetes. Any questions so far? Ooh, what is ingress? Good question. So we have a pod that wraps a container that gives it kind of a local network. We have a service that load balances across all of those pods, but we don't have a mechanism yet to connect from the outside. An ingress is that piece that allows us to map a particular host name to a service. So I'll connect to www.mysite.com, and that will land on this ingress. The ingress knows that if I went to www.example.com, I wanted to go to this service. And the service knows that it load balances across these pods. And so the service then pushes me, in this case, to this container or to that container if it's healthy and not excessively utilized. So that's that ingress, mapping a domain to a particular service. Great question, Scopa. This was a lot of fun to get to show you building stateful workloads in Kubernetes. You saw each of these code samples is actually just text. So you can grab these slides from robrich.org and just copy that text, that YAML, set it in place and start to use it in your application today. There aren't any images other than the network diagrams, so you'll be able to leverage the code that we saw today. If you're watching this video later, hit me up on Twitter at rob_rich, and let's dive in. You can grab the slides right now at robrich.org. And for those of us here live in the event, what are your questions? What are your thoughts? What are the other Kubernetes resources that you really enjoy when you get to that next level of getting past the Kubernetes 101 discussions?
Rob, now database stays in containers, right? That is the industry standard.
Yes, databases are moving into containers. There's actually a mechanism, I'm not sure if it's Azure sponsored or SQL Server sponsored, that allows you to run SQL Server inside of Kubernetes containers. Back that with volumes to get the persistence beyond pod restarts. I'm not sure if they use a stateful set to keep the various shards of SQL Server in place or if it's just a single node. But yeah, SQL Server running in Kubernetes is definitely a thing.
So that is the case, then it will support everything like clustering of the SQL Server as well as always high availability.
Exactly.
Well, it's
My
going to be
SQL Server cluster nodes are just pods running inside of my Kubernetes cluster.
That's a Linux flavor of SQL, right? I don't know how much does that have anyone know if that's like got all the full features that you would get on a Windows version?
It actually does, except for those features that don't make sense. So it has all of the SQL features. It even has SQL CLR, which to get a .NET framework runtime running in a database on Linux, that's just amazing. It has SQL agents, it has replication, log shipping, all of those things. It doesn't have SSRS because that requires IIS, and it doesn't have reporting services because that also requires IIS. No, SSRS requires Active Directory, and that's why it doesn't have it. But aside from those two features, then it has everything.
I recall it's basically a virtualized version. So it's interesting getting it to run on Kubernetes.
Yeah.
It's like virtualized on virtualized.
Yeah, exactly.
Microsoft
Microsoft is actually committed to saying that SQL Server on Windows and SQL Server on Linux will both be full featured going forward. Any new feature that gets added to either will get added to both.
What are your thoughts on Dapper? Have you used it?
Dapper is really interesting. Dapper creates an abstraction layer over the top of data stores or event stores or other resources. And it allows you then to have a really simple REST API that you can just hit to be able to get at those data stores. The implementation then is you might be able to replace a data store. Now, today I want an event store and I want it backed by Kafka. Tomorrow I may want it backed by Event Hub. And so that's kind of magical. It uses sidecars inside of Kubernetes to be able to create that abstraction layer to give you that REST API into those resources. So from that perspective, it's amazing. But I remember similar arguments back in the day of saying, let's create these abstractions in case I ever wanted to move between SQL Server and Oracle. And I never did. So, because it's this lowest common denominator abstraction layer over the top of these things, I wonder if there's ever any full features that I'll want to take advantage of in a particular thing that I can't because I've got the Dapper abstraction. I don't know. I haven't gotten deep enough in my experiments yet to know if I'm going to hit that wall.
It may be a hype that just goes away. Who
Yeah.
knows?
It's kind of interesting. It's like half service mesh,
Right.
but without security. And to me, it's like, but that's kind of the point of a service mesh is security. So it is that abstraction of resources, not a service mesh.
Mm-hmm. So you find service mesh much more valuable, I assume, right?
They solve different problems.
Both are kind of sidecar approach, right? They're both.
Yeah, they both use sidecars to implement their behaviors. Service mesh does so for security reasons. Dapper uses it for abstracting resources into REST APIs.
Mm-hmm. Thank you.
I've actually got an experiment halfway built where I have one container that accepts a post and saves it to Kafka. The next container reads the Kafka messages and saves it to Redis. The next container reads it from Redis and shows it as a different website. And all of that is running inside of Dapper. So I'm no longer connecting directly to Kafka or to Redis. I just kind of say, hey, Docker, give me a event queue data store. Or, hey, Docker, give me a cache. And not Docker, Dapper. And Dapper says, here you go. I've got a cache for you. Oh, by the way, it's Redis, but you don't know that.
A nice abstraction. Yeah.
Yeah.
Thank you very much, Rob. It was an excellent talk.